Hi, and thank you for your time today. My name is Z Gazak, and I'm an astrophysicist and deep learning engineer in the Pivot SDA AI and Autonomy Sandbox. Our team supports the Space Systems Command of the United States Space Force, and we are tasked with bringing state-of-the-art deep learning techniques to the increasingly congested and contested orbital regimes surrounding Earth. Today I'll focus on the problem of positive identification. Put simply, maintaining a safe operational environment in space requires knowing the location and identity of satellites. SpectraNet offers a solution to the problem of identification. For large objects in low Earth orbit, spatial information can be collected from telescopes on the ground. Trained analysts or convolutional networks are highly effective at identifying observed targets in those frames. Objects in geostationary orbit, which are much farther away, cannot be spatially resolved from the ground. The salient spatial information is lost. To identify satellites in these orbits, a new sensing modality is required. In this work, we embrace spectroscopy. By dispersing light, which would otherwise form the fuzzy dot on the left, we expose the spectral energy distribution of that object. Light of different wavelength, or color, falls into a smooth distribution along the horizontal axis of the example to the right. While an image resolves spatial information, a spectrum resolves the physics of an object's material and state. Unfortunately, this observing modality is non-intuitive and out of the reach of even extensively trained analysts. Furthermore, the first principled physics governing reflection, absorption, and re-emission by manufactured and assembled materials is too complex for the quantitative, physics-based spectroscopy used in modern astrophysics. We developed 3 datasets to explore and characterize the potential for learned spectroscopic solutions to the problem of positive identification. We simulate a 64-class dataset with 2,000 observations per class at high signal-to-noise. This dataset represents a future dedicated SpectraNet-powered technology. After success in that experiment, we collected a non-sky dataset at moderate signal-to-noise and generated a synthetic dataset to match. These datasets are available at the Unified Data Library as linked, and any of the authors on this paper can assist with access. The frames to the bottom right represent a small subset covering the signal-to-noise distribution of our on-sky dataset, which is plotted on the bottom left. Here we provide observational constraints on a large-scale SpectraNet deployment. In order to deploy a performant inference model, the sensor requires as few as 50 examples per class, and operators can expect significant gains in inference accuracy with ongoing operations and periodic retraining. To provide well-calibrated and statistically relevant inferences, we trained large ResNets with dropout during training and at inference, thus ensembling in place. Multiple inferences on a single example explore the Bayesian posteriors of class likelihood and provide tunable inferences for risk-aware decision-making. Our on-sky observations provided a 9-class dataset of 100 to 300 observations per class, and trained ResNets returned accuracies exceeding 70%. These results are plotted in the narrow window to the left. This matched experiments performed in simulation and provided an experimentally measured minimum signal-to-noise needed to perform learned positive identification in the field. We found that stochastic weight averaging and its family of Bayesian solutions outperform point estimate models in almost every experiment and provide better calibrated inference in every case. The additional burden of compute during training and memory footprint at inference is a trade-off justified by gains in the practical application of this technique in the field. You've probably noticed just how little data is required for generalization here. We hypothesize that the spectrograph offers a physically principled pre-processing step which smoothly orders information before extraction by the neural network. For example, a spectral feature caused by sunlight reflecting off of aluminum will always occur in the same position in each observation where aluminum is present. This significantly simplifies the information mapping which must be learned by a network architecture and reduces the data overhead required for generalization. Today's society is deeply tied to space-based technologies, and maintaining a safe orbital environment is critical. This work presents one piece of a large portfolio managed and performed by our team. Thank you for your attention. We value the opportunity to present at this forum.